Our speaker for today is Professor Abhijit Mukherjee. Professor Mukherjee is a professor at the Department of Geology and Geophysics and the School of Environmental Science and Engineering at the Indian Institute of Kharagpur, Indian Institute of Technology Kharagpur. Dr. Mukherjee holds a degree in hydrogeology from the University of Kentucky, USA, and he has completed his postdoctoral work at University of Texas at Austin. Previously, he has served as physical hydrogeologist at Canada at Alberta Geological Survey in Canada. Professor Mukherjee's main research areas are physical, chemical, and isotope hydrogeology, including numerical modeling, computational contaminant transport, and water policy applications to society. He is known for his studies on geological and human source water pollution, that includes arsenic, fluoride, sanitation-borne and emerging contaminants in more than a dozen countries, water quantity estimates, including the application of advanced computation and artificial intelligence techniques. He has published more than 140 international journal articles, in addition to more than 200 book chapters, conference papers, and proceedings. He serves and has served in an editorial capacity in the Journal of Hydrology, Applied Geochemistry, Groundwater for Sustainable Development, Journal of Earth System Sciences, Scientific Reports, Water Resources Research, ESNT Letters, and ACS ESNT Engineering. He is presently serving in the Council of Geological Society of America. His previous edited books include Groundwater of South Asia, which was published in Springer in 2018, Groundwater published by Elsevier in 2020, and Riverine Systems, which was published by Springer Capital Publishing in 2022. For his work, among several accolades, Professor Mukherjee has been conferred the National Geoscience Award in 2014 by the President of India, the Kharka Award in 2020 by the International Association of Geochemists. He was inducted as a fellow to the Royal Society of Chemistry in 2020, the Geological Society of America in 2021, the Geological Society of India in 2023, and the American Geophysical Union in 2023. He was named by DST as top 75 leading Indian scientists and experts under the age of 50. He was also awarded the Shanti Swarup Bhatnagar Award prize in 2020, which is regarded as India's highest award, and the 2023 AGU DL Award awarded, which is regarded as AGU's highest union honor for researchers working in developing countries. The stage is all yours, Professor Mukherjee.
I'll be talking about geogenic groundwater contaminations, more from a perspective of drivers and management. Now, this is a topic that are explored by scientists from across the planet in various domains, including groundwater specialists, including civil engineers, water resource engineers, agricultural specialists, and so on. So what I'll try to do here is, in the next 45 minutes or so, try to integrate that knowledge into one thread and try to get back how we can manage it. Okay. Yeah. Before going further, I would like to briefly acknowledge all my collaborators over the years. So the work that I will be presenting is actually just not mine, but also working with my collaborators. And here is a snapshot of some of the organizations that I've worked with in the last about 20 plus years. And their work are also represented in the slides that I'll be showing. So before I go for groundwater contamination, I possibly need to explore a little bit on what groundwater issues are. Now, groundwater is the largest resource of fresh water in this planet. Beside the oceans, where you have a lot of saline water and the polar ice caps, the rivers are nominal. Groundwater becomes the primary source of drinking water for the 8 billion plus population in this planet. However, it comes with a lot of issues. And as a hydrogeologist or environmental scientist, I would like to highlight those issues in brief. The first one is water scarcity. And as we know, like the summer is rolling up in the Northern Hemisphere, these kind of photographs will start seeing in the media quite soon enough. But at the same time, you have different other parts of the country, the nation, and as well as the globe, where you would see a lot of water excess issues, and you have water scarcity and water excess almost simultaneously, suggesting that there is a management issue that needs to be addressed. However, whether it's a scarcity issue or an excess issue, it eventually translates to drinking water security issue. Because, for the survival of us in this planet, one of the primal thing that we need is drinking water, clean drinking water. And either of these two issues that I just talked about would jeopardize the availability of that drinking water. And then in today's time, we have a lot of talk on the climate change. Now, I am not a climate change scientist, to be honest. And I don't really understand what climate change is going to do. I don't think many people does. But one thing we are all certain that if climate change is going to happen, one of the first victims of climate change would be the groundwater resources. Now, one thing I did not talk about is groundwater quality. And this groundwater quality includes groundwater pollution or contamination. And the collage of photographs that you are seeing on the screen are not taken from Google, but I shot it myself from the various field work that I've done over the years. And as you can see, like people across the world, specifically in South Asia, are actually suffering from drinking just bad water. Much of this water sourced to groundwater, which tells you that there is a huge amount of work that needs to be done from a scientific perspective, as well as from societal sustainability relevance, which can address these water quality issues. Now, this is more obvious as we're approaching 2030, where that we are supposed to achieve the UN Sustainable Development Goals. Goal number 6 is access to clean water and sanitation. So, which is very obvious that it is one of the primal goals that we have to achieve in order to achieve our Sustainable Development Goals. Now, if you look more carefully, you'll see that each of the other 16 goals of the 17 SDGs, they're also connected to the access of clean water and sanitation in some way or other. So that brings us to the water pollution issue in a greater context. Now, this shows only for India, but this is a story all for across the world. And give and take 300 to 500 million people at least are known to be surviving in areas with poor water quality. When I say poor water quality, it's 70 to 90% groundwater, which means that groundwater pollution is something that is not just a concern for South Asia, but across the world. So if you look in the media, if you look in the reading media or the internet media, you will see a lot of publications and newspaper reports, media flashes that comes out, which all talks about the water pollution issues, groundwater pollution issues. And this groundwater pollution, they spreads across the continents, from North America to the Asia, they're everywhere. And people from the US EPA to the Chinese government to the Indian Pollution Control Board, they're all concerned about how to visualize and then how to manage the groundwater pollution issues. So what the question should be is, what are the sources and drivers of groundwater contamination, and how do you manage it? So in the talk today, in the next few minutes, I'll try to address some of these questions. So I'll begin with sharing a list of 10 substances. This is a list from what we call the Agency of Toxic Substances and Disease Registry, ATSDR, published in collaboration with US EPA, where they list 100 substances which are, like really harmful to human health. Most of them found in water, groundwater. So these lists that I'm showing you are the first 10 as of 2019. And again, this list has not really changed, at least the first 3 in the last 20 years. The list is topped by arsenic. As you know, it's a geogenic pollutant, mixed by lead and mercury. And then there are a lot of other organic chemical names, which tells you that geogenic pollution in some way or other can actually end up in your glass of drinking water, eventually getting you sick in a short to long term, creating up to death. So it tells you that proper scientific studies needs to be done in order to understand the level of occurrence, the existence of these geogenic contaminants, as well as the strategies by which we can manage them. Now, to do that, we first need to understand groundwater contaminants. And groundwater contaminants are of two types. They are geogenic or natural, or anthropogenic or human sourced. Now, most of the times, many of the times, people actually talk about, small scale pollution that includes agricultural source pollution or urban or industrial pollution, which both can end up to the groundwater systems. However, in today's talk, and I can assure you that it's a pollution in a much, or contamination in a much larger scale, are the geogenic pollution. These geogenic pollution are also regarded mostly as what we call non-point pollution, which means non-point source pollution, which means that you don't exactly know where they're coming from. And that makes it much more difficult to manage, to remediate, and to use it for clean water sources. So the challenge is, like, how do we see the geogenic groundwater pollutants? The challenge is in multifold. The first challenge is the scale of the groundwater. So the geogenic groundwater pollution or contamination, I'll refer henceforth as GGC, geogenic groundwater contamination or contaminants. And the first thing that we need to understand is the scale of occurrence. Now, various organizations and researchers over the years have actually mapped the occurrence of geogenic contaminants. The map I'm showing you is one of the first one that was published in the year 2002 by the British Geological Survey through their pioneering work in Bangladesh, where they mapped arsenic across the country. This was really a pioneering work in a sense that it was still kind of, in an adolescence period of geogenic groundwater contamination studies when this report was published. And subsequently, some millions of papers were published on these issues. So what you look at are different patterns in this map, from the cold blue color, which shows, almost negligible pollution, to areas with bright red color, which shows, a very elaborate levels of pollution. But these occurrences, these patterns are in a very regional scale. Now, if you zoom that up, and if you look at point data rather than like a spoon end of data, you see that these occurrences may not be as regional as it looks like. So if you go to a local scale to a village scale, you see that there are a lot of discrepancies. Although in broad sense, you can say one area is more contaminated than others, but on a village scale, in a community scale, there can be differences. And it becomes a challenge to understand, this scalability issue, like coming from a more regional scale to a local scale and local scale to a regional scale. And that's where makes the science of geogenic contaminants a little more challenging than other contaminants. So the way I want to look at it, I try to look at it, is that the geogenic contaminants are actually present in nature in a nested way. The first occurrence is in a global scale, which shows us, which can be elaborated to understand the big picture. But then that can be telescoped in for local scale pollution. Eventually, what matters is the community scale and the well-to-well variability. And what is interesting is to to scale out and in among these various scales. And in the next few slides, I will try to highlight those scalability issues a little further. So the first one I would like to show you is the occurrence of arsenic, as we know. And again, like new studies are coming up almost on a daily basis. So this map is changing. But broadly, by and large, this is how the distribution of geogenic groundwater arsenic is present across the globe. What you would see that there are major areas in North America and South America and Asia, mostly South Asia, where you do see these boxes or rectangles, which are known to have groundwater enriched with arsenic. Similar thing can be also seen for the fluoride, where again, North and South America large areas are actually polluted, followed by some areas of Asia and Africa, and selenium and uranium. So I'll be broadly talking about these 4 contaminants, emphasizing on arsenic and fluoride a little bit more. So these maps kind of gives you an impression that the contamination, so the point to be take home message is that the contamination issue is not just into one country, limited to one country. And it is actually, transnational to the continents actually. But, just looking at this map, can we really see any pattern? And for a long time, I personally also kind of, thought, okay, the map might be these are all local issues, and we should look at them in a more local sense. But then, one of my colleagues, he mapped the occurrences of arsenic and fluoride with machine learning tools like AI tools, and then we get to see a more elaborate occurrences of these contaminants. And as you can see in this map by Pogorski, he mapped out the arsenic probability across the planet, arsenic and fluoride probability across the planet, like through these colors, the red for arsenic and the blue for the fluoride. Now what you get to see is that there are few things that's showing up. But still, it's kind of, very national thing, right? People study arsenic in India, arsenic in China, fluoride in Africa, uranium in the US, and so on. So it becomes a very national thing and very local thing. And that let me think, this contaminant in a more, elaborate way. And I love to show this slide with the parable of the blind man and the elephant. Are we all being the blind men that we're trying to see the elephant? And we're just trying to touch the different sides, different, body parts of an elephant, and using our imagination to see what the contamination issue is. So as this famous poetry talks about, the 6 men went to see the elephant, but they were all of them were blind. So we are not able to see the full picture. So what is the full picture? Well, let me now put all of these contaminants that we just talked about in a global geologic or tectonics framework. And it starts making sense. We get to understand these orange areas, which are the arsenic, and the pink areas, which are the fluoride, as well as the selenium and the uranium, which are of lesser context or lesser content extent even. You would see that they very well fit a geological model. Arsenic specifically exists in what we call the mountain belts or orogenic belts, and the sediments that were deposited out of the orogenic belts in the river valleys. Whereas fluoride specifically are present in areas which are known to be geologic shields, ancient land masses. And what, like all these other maps that I showed you can be integrated to this one map, which kind of gives you the context that none of these observations were standalone. And actually, what we were observing were pretty much doing the play of the 6 blind men. And it is actually the global geodynamic processes that are influencing the existence of these contaminants in the groundwater systems. So what is the model? Well, we start with magma. Now, I'm a geologist, so maybe I'm a little bit inclined more on the geological sides of it, but I hope like I'll try to make you understand what the processes are. So it starts with the arc magma, which is the magma that gets generated when two continental plates, or one oceanic plate and one continental plate of the Earth's crust would collide, and eventually resulting to the crystallization of the first level of minerals, which are called the high temperature minerals. These high temperature minerals would go through some geogenic processes called chemical weathering, eventually resulting to what we call the two phases of minerals, the stable minerals and the metastable minerals. In the stable minerals, you have arsenic and the other geogenic contaminants are kind of recalcitrant, so they are in the structure of the minerals, whereas in the metastable minerals, they are kind of physisorbed, so they are kind of sorbed quite easily. What it results to in millions of years, so these processes I'm showing you, they take from 2000s to millions of years. So you have to keep that context of time also, while understanding this model. So these minerals eventually would be transported in dissolved phase or to aquifer solids. Aquifer is the geologic media where the groundwater is present. And this is here where these contaminants would now get sequestered as sediments, in sediments. So the sediments now becomes the immediate source or provenance of all these geogenic contaminants. So under conducive conditions, geochemical reactions, which can extend from simple acid-base reactions to pretty complicated redox reactions, these sediment sequestered geogenic contaminants would be now released to the groundwater. And it will stay in the groundwater until there is a change in the geochemical condition and the contaminants are resequestered back in the sediments. And this cycle continues. So in a nutshell, in a very, very layman's way, this is kind of the global cycling of the geogenic contaminants from the mantle, like where all these magma are present, to form the minerals, the early minerals, which are very high temperature minerals, to form the immediate source of the geogenic contaminants to the contaminants in the groundwater. Now, this is just a model. How do you know that it's really happening? Well, through our studies across the last 20 years, we went to the Himalayas. Like why Himalayas? Because as I'll show you in next few slides, that South Asia is one of the most well-known example of groundwater contamination, and Himalaya is the water tower. It's also regarded as the third pole, because all the South Asian countries, which holds almost like 1/3 or more of the global population, actually gets its sediments and water from the Himalayas. And what I'm showing you are the potential sources of the arsenic in the Himalayas that we located in what we call the Indus-Sangpo-Sucha zone, that eventually would be weathered and eroded and transported to the river systems like the Indus, the Ganges, and the Brahmaputra, and other rivers. So we believe that these are the sources of arsenic in South Asia. On the same note, if you go to Africa, East Africa, where there is a huge fluoride problem, you will see that the African fluoride is again connected to the geodynamic systems. And there are, so this photograph that I'm showing you is between Mount Meru and Mount Kilimanjaro, which are all both known to be volcanic geologic formations, have their rocks, conducive of releasing fluoride to the groundwater under conducive environment. And it is now kind of established that based on the occurrences of the volcanic source sediments that are present in the stable shelves of the East African ridge, the fluoride in this groundwater are present. So it is telling you that you need to understand also your rocks to understand your chemistry, and your chemistry to understand the pollution, which is eventually going to impact your health. So in this diagram, in this slide, I'm showing you the example of some of the source and sinks that we have identified across the world. It starts with the source in the Himalayas, the Himalayan rocks that are known to be having high arsenic rocks or minerals, followed by some lava from the Andean mountains in Argentina to the geothermal springs of Chile. Same way, if we talk about the sink, we get the Red River sediments from Vietnam, the Mississippi Delta sediments, Mississippi River Delta sediments from the US, or the Meghna River in Bangladesh, where we can see that water is getting discharged, groundwater is getting discharged, known to be releasing the arsenic to the from the aquifer to the river. So this gives you a snapshot of the types of rocks and sediments in which you would think the original source and the sink of the geogenic contaminants would be located at. So if we tie up all these observations, it gives us a very interesting model. So I call it the big picture. And what we're looking at, this snapshot of like a very hypothetical topography, you see that there are these rocks on the left, which are the magmatic deposits of the uplands, which are whitish colored rocks or felsic rocks, which eventually would be eroded and would be brought down by the rivers to the ocean. And in the process, you also see the groundwater systems that are flowing from the recharge zone to the discharge zone that you can see in the cross section. Now, what it's also showing you, the chemical reactions that might be going in, releasing this pollutant or contaminants from the source rock or sediments to the groundwater. So if we want to summarize, the arsenic and like arsenic as in arsenic +5, so in a redox rate of +5, uranium and selenium, they would be released through redox-related reactions, redox-induced reactions in the more recharge zone of the groundwater system, whereas arsenic 3, which is arsenite, along with sometimes uranium, you can observe in the discharge zone, which is the more anoxic zone, because of again reductive dissolution of minerals. So the release of these elements or these ions like arsenic, uranium, and selenium, they are actually dominated by redox reactions, whereas fluoride and uranium to a certain extent are also impacted, or the release is impacted by acid-base reactions, or what we call silicate weathering. So these acid-base reactions of rocks, ancient rocks, actually releases out the fluoride or the uranium from the bedrock to the groundwater. So this image hopefully shows you a composite view of why you are getting arsenic or selenium or fluoride or uranium, where you are getting them. So if this is a more hypothetical situation, let me broadly bring in a case study. A case study to elaborate that while those are the big pictures, can we see or observe some of these phenomena even in a real area? So let me talk a little bit on the arsenic contamination in South Asia. Now, how big is the contamination? Well, in the year 2000, Alan Smith referred this as the largest mass poisoning in human history. Never before so many people together got to be known to be poisoned by some natural sources or even human sources. So present estimates are somewhere between 100 to 300 million people across South Asia are actually drinking contaminated groundwater. So which are the areas? Well, we did find from literature as well from our studies that all the Himalayan sourced river systems, the Indus, the Ganges, the Brahmaputra, Meghna, Irrawaddy, Mekong, and Red, across South Asia and East Asia are known to be polluted by geogenic contaminants, which tells us that there is something that is missing and we need to explore that. Well, here it is. So I'm showing you the groundwater systems of the Indian subcontinent or South Asia. You can refer it either way. You do get to see that on the left-hand side, you do have these colors representing the different aquifer systems or groundwater systems. And what you're looking at, there are two broad classes. One is the bright blue and one is the deep blue in the left-hand side map. And the bright blue indicates the Gangetic, the Indus, and the Brahmaputra basins, whereas the deep blue indicates what we call the crystalline aquifers, or the South Asian or South Indian or cratonic aquifers. So the older rocks, basically. So while the bright blue are indicative of the sediments that were blown down from the Himalayas, this deep blue indicates the older rocks. Now, what is interesting is on the map to the right, you see that the extent of the geogenic contaminants that we know as of today that are present, the blue is arsenic, the yellow is fluoride, and the stippled is saline or brackish groundwater. They do follow this pattern of the geologic formations that I showed you on the left. How good? Well, let's look at it. So let me show you just for for the sake of this presentation, just arsenic. And this is a map that well, couple of maps that we published recently, integrating about 3 million locations from the Government of India databases. What you're looking at the map on the left is the predicted arsenic probabilities that are found out from these 3 million locations. On the right hand side, you also get to see the arsenic hazard map. So the places where you think like more than 10 microgram per liter, which is the threshold, the WHO MCL for arsenic is, where you find people drinking or exposed to high arsenic groundwater. So if I go by the population, so you now see like what is the population that would be exposed to this high arsenic groundwater. The right hand side is a geologic map of the area. Now, how is this then connected? Well, let's look at it. Well, this northern side, where you see most of the arsenic pollution in South Asia is, they are actually geologically or like from a tectonic side are known as the Himalayan forelands. These are the Indus, the Ganges, and the Brahmaputra basin, where the sediments are coming from the Himalayas are getting deposited, so, which kind of now suggests that it is the Himalayan sediments which are the sources of the arsenic. But then you also do get to see some locations of arsenic in the central part and the southern part of India. So how are they connected? They are not connected to the Himalayas. Well, they are not to the Himalayas, but to the geology. So the area that I'm showing you with the black box now is known as the CITZ, the Central Indian Tectonic Zone. This is a very ancient geologic structure. Again, like it went through the geological evolution, where you would see all this arsenic potentially because of the similar processes that are happening in the Himalayas today. Of course, you don't get to see big mountains in these areas because these are very ancient mountains which are now subdued because of geologic processes. And then in the southern areas where you do see the arsenic, these are the areas with the gold fields. So you know that gold is like a chalcophile, just like arsenic, and they kind of coexist. So wherever you have gold fields, there is a probability that you also have the arsenic in the groundwater. So this gives you a context to understand how the groundwater arsenic in at least India and also South Asia would be kind of related to. But then it is not just that. There are these chemical reactions. And what this kind of conceptual diagram shows you is what would be the reactions that are happening in the subsurface, releasing out the arsenic 5 and arsenic 3, respectively, in the recharge zone and the discharge zone. So what are the mechanisms that people have talked about? Well, over the years, over the last about 30 plus years, people are speculating different mechanisms. The first one is oxidation of arsenopyrite or pyrites that are present in the sediments. Second one being competitive displacement of phosphate ions. And the third one is a microbial induced reduction of iron oxyhydroxides under anoxic condition with possibilities of reoxidation. Now, all these three probable mechanisms have been kind of promoted by various authors in few 100,000 publications. Literally what I meant is few 100,000. And some people have argued, for number 1, some people number 3, but by and large, number 3 is regarded as the more acceptable hypothesis as of the day. But again, we don't know for sure. So when we did some studies, we based on the geochemistry of the water, geochemistry of the groundwater, we came up with this understanding that it is just not one process, but a combination of processes. And yes, redox is the number one driver, but you can also have ionic competition, something called counter ion effect, and pH source disruptions. So what it tells you that yes, in the textbooks and the papers, people are very eloquent in saying, okay, this is the reason why these geogenic contaminants is present in the water or the groundwater. But in reality, the processes are much more complex, and it needs much detailed understanding of what's going on. But then I have not talked about human. Well, there is this influence of pumping, and our study showed that arsenic particles, which would in nature would take 250 years or more to travel from like a point of existence to a pumping well. Pumping well means where you're getting your drinking water, like your drinking water source, can actually short circuit and arrive within 5 years, which means that you are literally having up to 40 to 50 times acceleration of the movement of the geogenic contaminant molecules to be moving in the subsurface just because of human induced pumping. So it is just not easy to explain this contamination from a natural perspective, but you also have to integrate the human perspective. So our model for looking closer. So when we try to show you the big picture, it is a picture that is kind of dominated by the geology and then kind of controlled by the climate and the geomorphology. Whereas when we are talking about looking closer, we are talking about the variabilities from well to well, and we are talking about processes that are going, biogeochemistry, the local, very local geology, as well as the human pumping, the human influences like land use, land cover change, and so on. So while the geogenic contaminant and the existence of the geogenic contaminants or its occurrence, we can predict on a global scale to understand its occurrence in a very local scale. We need to understand the local processes much more further. And now many people did argue that actually it's the local scale processes that are more the culprit in sourcing your the contaminant to your glass of water. I differ from them, and it's a combination of both the sides, both the big picture and the model for looking closer. Anyway, if you have sorry, if you have the problem in your backyard, you need to solve it, and that's where the management of the diseases come from. Now, unlike um, uh, the point source contaminants, which are more human source contaminants, in those cases, what the source of the contamination is. So you go there, plug it, and the contamination is mostly resolved. Now, in case of geogenic contaminants, by now, hopefully, I have kind of tried to explain you that it's in a much larger domain than what we human can manipulate with, because it's the Mother Earth that is playing the tricks. So we cannot really go and plug it. Instead, we have to think about other mechanisms, other management strategies. So remediation, yes, but I think management is a better term. So this flowchart kind of demonstrates that. And you can have these geogenic contaminants, and the occurrences and distribution, and ideally you also know the drivers, can then be designed for mitigation strategies or management strategies. And you can either go for treatment. Treatment means some kind of engineering solution, either in situ or ex situ, or you can go for other natural source or natural based solutions like shifting to safe sources, like well switching, like switching to other sources. But then each of these are some way or other influenced by the human behavior and society. So we cannot disentangle the human angle away from even the mitigation or the management strategies. So in many countries, these management strategies works extremely well. In other countries, they don't. And it's not the technology or the science, but it's the human. And this is where I think I cannot emphasize further than to say that science policies need to be human oriented, and they need to be kind of compounded or added with human behavior and the societal requirements. So it's very important that science, policy, and human behavior are integrated into one thread. And when I say they fail, they fail. And studies from Bangladesh showed that different technologies over the years have failed from from 80%, like 60 to 80%. And most of these techniques have failed other than natural-based solutions. Now again, they are not a perfect solution, but they are better than many of the other solutions that people have used over the years. So engineers, mostly chemical engineers and civil engineers, they have designed all these treatment facilities, and they are being run across the world, big money, the water industry. But then, or this plot kind of shows you the summary of that. So I'm supposing most of you would be quite aware of the treatment strategies. So let me highlight a little bit further on the arsenic safe tube wells, which possibly is something new for many of you. A study from one of our former students showed that it can be easy, and you can start with just looking around. You don't need any instrument. I'm sure, like all of you know, that tube wells do have platforms, right? Cement platforms. In South Asia, they are extremely common. In other countries, they are also available. In Africa, I know they exist. In Latin America, they exist. Now, if you know that there is arsenic, let's take the example of arsenic, and you know that arsenic is present in the groundwater, how do you know like which well does have arsenic or not? You can go for elaborate lab, or some sensors that can possibly give you like a ballpark number, like 50% plus minus. But can you use something else, some other proxy? Now, this study that we did showed that if your platform color is black, you have less than 30% chance that that well, the drinking water in that well, has arsenic. Whereas if they are mixed color, and even better, red or brown, you are reasonably certain that your groundwater has arsenic. More than 80% certainty. Why? So what are these color for? Well, these color actually are indicative of the subsurface geochemistry. This black color indicative of manganese oxides, whereas a red and brown color indicative of iron or more lower level redox processes. So you can look at the sediment colors, which are a manifestation of these colors that I just showed you in a platform. And if you have gray color sediments, you reasonably know that these aquifer are actually reducing. So this color actually is indicative of the redox state, whereas the yellow color actually suggests that you have a more safer groundwater system. So, strategies that were developed by my friend Prashant Bhattacharya from KTH showed that in Bangladesh, it was great. And, like the areas where you have these gray color sediments, you know that this would be polluted by arsenic, whereas the yellow or the white color sediments are less susceptible to having arsenic in the groundwater. So it shows you a very down to the earth, down to the ground method of identifying just from visual references that where you would have arsenic in the groundwater or not. But it's just not the visual references. If you do like pretty elaborate geochemical study or mineralogical study, you would find the reason. You will find the reason that in the brown color sediments, you have fan-model pyrites or other iron oxyhydroxides, which are actually holding back the arsenic, whereas the gray color sediments, they are mostly iron 2 oxides. Consequently, you have the arsenic released to the groundwater. And then you can now possibly pinpoint back your platform color to the color of the sediments in the subsurface and the potential pollution in the groundwater, indicative of the redox system. So this plot shows you how the redox is varying, and each of these platform color is actually establishing or indicating a pretty detailed redox-based reaction that is happening in the natural system in the subsurface, which is obviously not visible to the common people who are drinking the water. So what we learned? What we learned in the last 40 minutes plus? What we learned is that what we didn't learn. So if I started with this slide saying that, the blind man went to see the elephant, I can end it with the same poetry where it says, though each was partly in the right, all of them were wrong. So yes, people have been talking about all these processes, the drivers, the sources, but yet, very honestly, we are quite far away from integrating all this information. So let me show you the first possibility of integration into something called a DPSIR framework, which stands for the drivers, pressure, state, impact, and response framework. And possibly you can now see that these contaminants, at least to my view, are not just there because they are there. They are not sent by, some alien or, by some very religious reason. Now, in some countries, religion do dictate the water policies. The matter of fact is that the reason that the contaminant is there in the well is actually extremely geological and chemical. So the root causes can be, the allogenic processes, the geodynamics, whereas the direct causes can be the local scale biochemical processes that would influence the contaminant fate and cycling. The pressures is induced by the human includes the land use land cover change that would relate to the release of the arsenic or the other geogenic contaminants more efficiently. What is the outcome? The outcome is the widespread GGCs, the contaminants in groundwater, as well as the crops. I really didn't talk about the crops much, but the groundwater, the crops that are irrigated by these contaminated groundwaters would also bioaccumulate the contaminants. Consequently, if somebody is eating those crops on a more regular basis, there's a high chance that the contaminant is now going to get biotransferred from the groundwater to the crops to the human. And there are plenty of studies which kind of demonstrates that. So what is the impact? Well, the impact is very obvious. It's the reduced access to safe drinking water, and of course the food insecurity, and resulting to atopic to terminal health diseases. And obviously, as we human, we reside in this planet and we try to make this planet habitable. Knowing all these things, we try to create a response, and this response can be multifaceted. None of them are perfect, but together they can possibly give you a way to move forward. So, if this was the DPSIR framework in a layman's way, in a flowchart, this is how it should be looking like. So we are looking at scales, the scales of space and time. We start thinking as a primary driver in a geologic time scale starting from the geodynamic processes. These eventually resulting to the weathering and erosion processes that would transport the contaminants to the immediate drivers, which are the regional scale aquifers. And these aquifers, depending on the microbial-based biogeochemical reaction, would release the contaminants, which would eventually be picked up by the wells, the drinking water wells, the tube wells, in a community scale. And from that well, it would get transferred into a glass of water, resulting to the impacts in a more household. And these would happen in a decadal time scale from 10 to 100 years. But then we need to access to clean water. In today's time, accessing clean water is the next big thing. So we need to monitor them, we need to detect them, we need to remediate them on a daily time scale. So our response need to be calculated and calibrated based on the ground reality, based on the geology and the chemistry or the chemical reactions that are happening in the subsurface and the treatment mechanisms, based on those processes. So I'll end up my presentation with that slide, and I'll be more than happy to take any questions that you would have.